Last time we started talking about the most general type of FMCW radar, which is the MIMO radar, right? That's the case where you have multiple transmitter antennas, multiple receiver antennas, and then it enables you to, this antenna diversity basically enables you to determine the direction of arrival of targets with some clever DSP. So we started by introducing this idea of the virtual antenna array. And this is a purely mathematical construction. Basically, if you have a MIMO array which has N sub TX transmit antennas and N sub RX receive antennas, so physically you only have NTX plus NRX antenna elements, right? But mathematically, we showed that it is equivalent. And by mathematically equivalent, I mean essentially the signal that you receive from it is equivalent to a SIMO array, single input multi-output, where you have just one transmitter and you have P receivers, where P is equal to the number of transmitters times the number of receivers in the original antenna array. And then the way this virtual antenna array is constructed, well, it's important to know where these virtual elements are placed, what are the locations of them. The transmitter, you can assume it's at the origin, it's at 0. And then the positions of the P receive antennas, each of them is the sum of the positions of one of the original transmitters plus one of the original receivers. So the indexing is K for original transmitter antennas, Q for original receive antennas, and then P for the virtual receive antennas. And then that's the tilde also is so that we know when we talk about, the prime, the R tilde prime, that's the position of the, actually, is my notation inconsistent with the notes? I think I should remove the tildes here, right, to be consistent with the lecture notes. Maybe something like this. So the tilde is for the virtual array. Yeah, you can cross-check. But the point is, now we can basically do all of our DSP in the virtual in the signal model that we define on the virtual array. So the way it looks like is like, let's say physically you have a 2x3 MIMO array. So there's the two triangles show the two transmitters, and the three diagonal circles are the positions of the three receivers. So if you look, say, on your PCB, these are the positions that you see. So physically, you have only 5 antennas, 2 plus 3. But the virtual array would have 6 antennas, 6 receive antennas, which are shown by the squares here. And then there's 2 diagonal rows. How did I get this? Again, from here. You just add the positions of the transmitters and the receivers, and then you kind of get that shape for the virtual array. And then we showed that for the virtual array, basically the full signal model that we can work with for the entire end-to-end DSP pipeline is given by this. So the IF signal, so the signal after down conversion that you receive from virtual antenna receiver number index P is equal to this summation I from 1 to K. This is to account for receiving echoes from multiple targets, right? So say there's big K targets all simultaneously echoing back. So we're summing the signals received from all of them. That's just the superposition principle. So that's why there's a sum here. And then the signal from each target, it has what we call a spatial phase term, which is this e to the j big omega pi, p for the index, again, for the virtual antenna, I for the target. That's why there's double indexing here. And this term, I call it the spatial phase because there's no temporal aspect to it, right? It's just affected by the direction of arrival of the echoes. And then there's the temporal part, which is the SIFI of t. And this one, as you see, it has time dependence, but it does not have p dependence. So it doesn't matter which virtual antenna you look at. The waveform they receive, that the temporal part of it or the time dependency of it is the same. The part that is different between different receive antennas is this spatial part. And that's why we focus on this term when it comes to direction of arrival estimation. Specifically, this spatial phase term, omega pi, is given by this formula, which is basically your wave number minus wave number, 2 pi over lambda, times the norm of the position of the virtual element, or virtual antenna P, times sine of theta I, where essentially what we want at the end of the day is this theta I, because that's the direction of arrival of the target. So if you look at this, if you want to develop DSP algorithms that estimate basically theta I for you for DOA, it's important to know, basically, your algorithm needs to know what this term is, what the norm of the position of the antenna elements are, right? So the geometry basically matters. And geometry, by geometry, I mean these positions. So here, in this case, like the fact that they're positioned diagonally, that also affects the phases that you receive in addition to the theta I. So from this, you can see that like by changing the positions of the elements, it can affect the performance of your DOA, basically. And we'll see that exactly how it affects it today. To develop our basically algorithms, we went with the simplest geometry that you can think of, which is a uniform linear array. Basically, this here, for instance, is not a uniform linear array. Uniform linear array, all your virtual elements are on a line, and they are equally spaced. So if I were to like draw a ULA, basically all elements are like this, and the spacing, we call that D. So every two are spaced D apart, and they're on a line, and that's a ULA. So again, it's the simplest array geometry you can think of. And then we developed the DSP for that, and we showed that to find theta I for a ULA, you basically can just do another Fourier transform. From the signal model, we simplified it, and we showed it like another Fourier transform. Basically, can recover this theta I. Okay? So here is on the slide the end-to-end DSP for a MIMO FMCW radar. Okay, let's trace it again together. So this is essentially everything we talked about, not just DOA, range estimation, velocity estimation, target detection, and DOA, all the way to, so from raw signals that you receive from the ADC samples to the final image, which is, say, a point cloud, a 2D or a 3D point cloud. So you start with these IF signals, SIF1 to SIFP. So these are coming from the virtual elements. Or the other way you can think about it is each of these SIFs is coming from a combination of a transmit antenna and a receive antenna, right? So transmit number one transmitted, receiver number one received. Transmit number one transmitted, receiver number two received. So all those combinations, you put them or you collect them together, and that's one what we call a raw data frame. Okay, so you have three indices. You have your virtual antenna index, that's P. You have, of course, your ADC sample index that we call N, and we know we use multiple chirps in a frame. So you have your chirp index inside the frame, and that's M. Okay, so basically the data format that we work with, it's a cube, so you can populate them in an M by N by P raw data cube, and then you can start basically processing it. The way the processing is done, typically you first do your range and Doppler processing, so you can think of them as two basically individual FFTs, or you can combine them as a single two-dimensional FFT. Here we have shown them as independent FFTs. Again, mathematically it's equivalent. You can decide how you like to do it, but you do an endpoint FFT along the basically ADC sample index, or the axis, or the N axis. So that's your range basically are along the rows here. That's your range FFT endpoint. And then you do your Doppler processing. That's an endpoint FFT along the columns, right? And again, you have to do it for every slice, right? Like, again, I'm just showing these for the first slice, but after you're done with that, you go through your second slice, or second virtual antenna, and do the same. So for that, you do across rows, that gives you your range processing, and you go across the columns of it to do your Doppler processing. So you should go through the entire cube, all the slices. So after that, you're basically done with range and Doppler processing. You can do target detection with like fixed thresholding or a 2D CFAR. So that what that does for you, it basically chooses range and Doppler indices that we think contains an actual target, and everything else you can assume there's nothing there. It's just noise. So that's what we call L hat I and K hat I. So those are actual targets. And then for those L hat I and K hat I, so if I clean this a little bit, so let's say let's pick just one of those combinations. So let's say this cell here is one of those that contains a target. So of course, after processing, right? So this is one of those L hat I, K hat I indices. And then you go for your DOA processing, you basically go through the third dimension. So you go basically in across all virtual antenna elements. So that becomes a vector of length P that then you do an FFT on. And then that FFT essentially converts the virtual antenna index to a DOA index Q that we can then map to actual angles with a simple, transformation that we talked about. So that's your DOA processing. There's the third FFT essentially, and then on that you want to also detect, after you do that FFT, the third FFT, you look at its amplitude, and then you pick the indices that are basically above a threshold. It could be a CFAR threshold or a fixed threshold. That gives you basically the Q hat I's, which are indices for the DOAs of where you think the actual targets are. And finally, so at this point, you have basically three indices: one for Doppler, one for range, and one for DOA. So these are indices, and then you can map them to physical quantities, which is velocity in meters per second, range in meters, and DOA in degrees or radians. And that conversion, it's just, basically kind of like linear transformations, except for DOA, which involves a arcsine transform, as we saw. And by this point, basically, this is the end of your DSP. So you have detected your targets, and for each target, you know the range, you know the velocity, you know the angle. And then you can decide how you want to essentially visualize or represent this fully processed data. A common way is to generate a point cloud. So a point cloud, you basically use the range and the angles of the targets and put a point for every target in the 3D space and generate a 3D point cloud. Or a 2D point cloud, if you only have, say, azimuth angle, then you make kind of like a bird's eye view 2D point cloud. Sometimes I've seen that velocity is also used in the visualization. A very interesting common way is use velocity to assign colors to the points in the point cloud. Like things that are moving, you can show them in a different color. It just makes a more interesting, richer representation. Okay, any questions about this, the DSP of FMCW MIMO? Okay, and one thing to note is, again, there's different variations of it. This is most of this is kind of like standard vanilla DSP, but you would see different variations of it. Like another common one is you can see in the literature that sometimes this target detection step, the 2D CFAR, is omitted. Okay, and you basically feed everything into your DOA processing. That's fine, still works. And then after that, instead of a 1D CFAR, you do like a 3D CFAR across range, Doppler, and DOA, and in one shot detect where the targets are. And then if you do that, you can basically combine range processing, Doppler processing, and DOA processing into one 3D FFT. Okay? The point is, it wouldn't be very efficient because you would do a lot of FFTs where there is no target. So the reason I like this better is that you kind of make it more efficient by filtering out a lot of the data at this step with a 2D CFAR, and then for DOA only basically focus on where you think the targets are. But again, the point is there is variations of it. Also, as usual, very important to always remember the assumptions that went into every step of the DSP. So specifically, for instance, for the DOA, we made a bunch of assumptions, like the fact that you can do a FFT. It's correct only if you have a uniform linear array. If your array is a different type of an array, then this algorithm wouldn't work for it, and you have to rethink or find another algorithm that works. Okay, questions. All right, so one thing we haven't looked at is from our DOA algorithm, this FFT algorithm, what resolution we can expect and what is the maximum field of view that we get. So those are the two things. Exactly like the thing we did for range and velocity processing, that after we developed the algorithm, we looked at the resolution and the maximum range and velocity that we can get. We're going to do the same for this digital beamforming algorithm that we developed using FFTs. So let's look at resolution first. So let's look at basically two adjacent DOA angles that our algorithm can discriminate, call them theta q and theta q plus 1. So those correspond to two adjacent FFT bins, basically. That's kind of like the minimum angle you can discriminate with an FFT. So let's take the average of the two, so theta q plus 1 over 2. That's the average of the angles corresponding to those two FFT bins. Call that theta, and that's kind of like our angle of interest. So we want to see at that angle what is the resolution to expect. And then the actual DOA resolution would be the difference between theta q and theta q plus 1, right? So that's just the delta. As you shift one FFT bin, how much the angle changes. So we want to find this delta theta. That's our DOA resolution. So we know that there is a nonlinear mapping between the actual angle and the FFT frequencies. So if you remember, we defined this parameter f sub theta, which was equal to 1 over lambda sine theta, or make it more concrete. So f theta I was 1 over lambda sine theta I, right? And from the FFT, we actually find these frequencies, and then we apply the inverse transform to find the angles from the frequencies, right? So there was this sine inverse transformation. So using that, the sine of theta q minus sine of theta q plus 1, that would be equal to lambda times delta f theta. So delta f theta is actually the width of one FFT bin, which, as you know, is equal to the sampling rate, f double prime s, divided by the total number of points in the FFT, divided by p, okay? And it's just a scale by lambda. And the sampling rate, if you remember, for a ULA, uniform linear array, was just equal to f double prime s, was just 1 over d, where d is the spacing between the antenna elements, right? So every two adjacent antennas were basically a distance d apart. So then sine theta q minus sine theta q plus 1 becomes equal to lambda divided by p times d. What is big P? Total number of virtual elements in the array. D is the spacing between them. Okay, so but we want to find delta theta. We just apply a little, trigonometric identity. If you remember, have this identity, which is sine alpha minus sine beta equals this, which is 2 times the cosine of alpha plus beta over 2 times sine of alpha minus beta over 2. Apply this to this expression up here, and the left-hand side becomes equal to 2 cosine theta times sine of delta theta over 2. Okay? And the left-hand side we haven't touched. It's lambda over PD. So at this point, we are pretty much done. We just make the assumption that delta theta is a small, right? It's the resolution of our radar, and if it's a good resolution, that angle is a small. So for a small delta theta, you can approximate sine of delta theta over 2 by just the angle itself in radians, right? Delta theta over 2. So use that. So plug that in here, and then we can solve for delta theta, which is the resolution we want to find. It just becomes equal to lambda over p times d times cosine theta. Okay, so this is this delta theta. This is the DOA resolution that we can get from our FFT algorithm. Again, for a uniform linear array. Very important. This is not true for any arbitrary array. But this is very insightful. I mean, we did a bunch of math, but it's always, what's behind the math that is interesting and insightful and important, which is if you look at this, so we want delta theta to be small, right? We want good resolution, meaning small delta theta, okay? But here's first observation that is very interesting. Delta theta has this cosine theta term in the denominator, which means that the DOA resolution is not uniform across the field of view of your radar, right? If you look down bore side, that's where theta is 0, cosine theta would be 1, so you get best resolution there. But as you go to larger angles on either side, so as you go towards the edges of the field of view of your radar, this cosine theta term drops, right? Large theta, cosine theta becomes a small, which means delta theta becomes large. So you have worse resolution towards the edges of your field of view and better resolution in the middle, down bore side. Very important, okay? So it's non-uniform DOA resolution. That's insight number one. Number two is what can we do design-wise to improve the resolution of our radar? Well, lambda is lambda. It's kind of, it is what it is. I mean, of course, smaller lambda, which means higher frequencies, helps. We know that's always the case. Higher frequencies, better resolution. And that's true in optics. That's true in millimeter wave radar. That's true in acoustics, right? Sonar and so on. That's one of those, general physics, principles that higher resolution, higher frequency, better resolution. So that's one. But for the case of radar, you don't have much of a choice. Like if you're working at 77 gigahertz, that's, there's a little bit that you can vary lambda. But you would have a lot of flexibility in choosing P and D, right? P is the total number of antennas, and D is the spacing between them. So P times D is what we call your total aperture size, right? I mean, it's technically P minus 1 times D, but let's call it P is large enough, so that's your aperture size. And what I mean by aperture size is, again, if you look at your virtual antenna array, you have element 1, element 2, all the way to the last one, so that's like Rx1 to Rx number P. And the total aperture size is basically the entire span, like that distance that your end-to-end, your first element and your last element, how far apart they are. That's basically how big your full aperture, antenna aperture is. And bigger aperture, better resolution. Again, exact same thing as we saw in sonar, for instance. In sonar, when we were talking about transducers, if you remember, we said bigger transducer, aperture size means more focused, more narrow beams, better DOA resolution. Same for radar. This is also true in optics. I mean, for instance, in photography, if you've seen professional photographers have lenses with huge apertures, that's because that gives you better resolution. Again, same trade-off at a different wavelength, but here we see the version in basically radio frequencies. So summarize. Non-uniform resolution across the field of view, better at small angles, meaning down bore side, worse at larger angles. And also, to improve your DOA resolution, you need arrays with bigger apertures. Either more elements or space them further apart, bigger aperture, better resolution. Okay? Yes?
Can you explain a little bit more about what FS double prime is?
Yes, so FS double prime here, question is what is this term? So this is essentially the sampling rate of our signal across the antenna dimension. So if I go back where we were on the DSP slide, okay, so if you look at this basically data cube, right, if you look at the three axes, across each axis there is a sampling rate, right? So horizontally, the sampling rate is your ADC sampling rate. That's your n index. And then if you go down the columns, what we call the slow time, the sampling rate is the time between chirps, right? So when you have multiple chirps in a frame. And then if you go across the virtual antennas, the sampling rate is that f double prime s, which is dictated by the physical spacing of your antennas, right? So it's like kind of like the spatial sampling rate instead of a temporal sampling rate. Another way to think about it is, let me try to sketch it maybe on this slide that we were. So if you have, if these are the elements of your virtual array that are a distance d apart, okay? And then if you have some incoming echo wave at some angle from a target, essentially what these antennas give you, they're going to sample the phase of this wavefront, right, at positions that are d apart, right? So it's this f double prime s, which is equal to 1 over d, is the spatial sampling rate of your antenna array for the incoming echo, basically. That's how far apart you sample the phase of that incoming wave. And it matters because we are trying to estimate that phase. So, for instance, if you don't sample it fine enough, you could not find very high frequencies. So you kind of can see D should matter when it comes to the field of view of your radar. If D is too large, that means you're sampling too coarsely, so you cannot find high frequencies in your FFT, which means large angle of arrivals cannot be determined, basically. But back to your question, f double prime is basically the sampling rate along the antenna axis. It's a spatial sampling rate, not a temporal. It's a spatial sampling rate across the antennas. Okay, so that's about the DOA resolution. So again, to improve the resolution, you need to increase the virtual aperture size. We call that A, which is equal to P times the total number of antennas times the spacing, which is the total aperture size, basically. What about the maximum unambiguously detectable DOA? And that's basically the field of view. What is the maximum angle that you can detect? That, exactly like the case of range and Doppler processing, is determined by the maximum frequency that your FFT gives you, right? So the FFT, again, if the sampling rate is f double prime, right, in the FFT, if this is frequency, remember that FFTs are periodic with a period of the sampling rate, right? And here, because our angle of arrival can be positive or negative, the period that we choose to go from minus the sampling rate f double prime s over 2 to f double prime s over 2. So this is the period that we look at when it comes to finding the angle of arrival. Anything outside this, we ignore because it's just a repetition of this first period. Okay, so if you restrict your search to that, the maximum angle that you can find is basically half your sampling rate. Okay, so your f theta max is just f double prime s over 2, and then your angle becomes arc sine of lambda times that. Okay, and as I just said, what is f double prime? That's 1 over d. That's 1 over the spacing between your antennas. So your theta max becomes arc sine of lambda over 2d. Okay, here's another, again, math is math, but the insight here is to improve your field of view, meaning to increase theta max. Your field of view is technically 2 times theta max because you go from both plus and minus. So it's from minus absolute value of theta max to plus absolute value of theta max. So FOV is 2 times that. And to increase that, main thing that you can change in this is this D. So if you make your D smaller, if you place your antennas more closely, that improves your field of view, basically. Because of this, the most common choice for D is half a wavelength, because if you choose your D to be lambda over 2, what happens is that your theta max becomes arcsine of lambda over lambda, which is arcsine of 1, so you basically get the full 180-degree field of view. And that's as good as it gets, basically. Most common ULA, 99% of radar arrays you see out there, if you just open them up and look at the antenna, you would see a lambda over 2 uniform linear array, and that's exactly because of this. And again, this should make sense, exactly as when you talk about time series signals. If you want to be able to see higher frequencies, you need to sample them more finely in time. Here, if you want to see larger DOAs, we need to sample the phase more finely in space. So you need a more tightly packed antenna array with a smaller D to be able to see larger frequencies, and larger frequencies in this case mean larger directions of arrival. Okay, now what happens if your D is larger than lambda over 2 such that your theta max is, I'm just going to make up a number as an example. So if your theta max, this is a thought experiment. We have an array with some D, and the theta max comes out to be 50 degrees. Okay, so the full field of view is 2 times that, 100 degrees FOV, right? FOV, 100 degrees. And now I take that radar out in the field. What happens to the targets that are outside this field of view? Like if I have a target at 130 degrees, which is a very strong reflector, like a corner reflector, what would happen? Do we not see anything in our process data cube? Do we see something? What do you think will happen? Anyone?
The reflector will be seen, so you'll see a smaller angle, like something like 80 degrees or so.
That's correct. So we will see something. So let's see what will happen. So here, if you look at our DOA FFT in this case, right, we said we are going to look from minus F double prime S over 2 to F double prime S over 2. Now, in terms of angles, we said that in this case, this corresponds to 50 degrees, and this is negative 50 degrees, right? The theta that correspond to those frequencies. Now, again, FFTs are periodic, right? So as the angle DOA of the target is increasing, let's say on the positive side, so there's going to be like a peak, and it's going to get closer and closer to that 50 degrees. As it crosses, let me use a different color. As it crosses our 50 degree, so if I have a target that is physically at 70 degrees, remember, we are always looking at this first period. So what happens is that we'll see the earliest peak from the previous period that is now showing at a very small, a very large and negative angle, right? So you will see something, but it shows up at the wrong DOA for you, and that's called wrapping. Again, there's this periodic signal, and things don't disappear, they just wrap around, right? FFTs are periodic. So that's a big problem, right? So very important. It's not like if you design something and you found a FOV of 100 degrees, you're fine. Anything that's outside 100 degrees just doesn't show up. No, they actually will show up, and they will completely mess up your radar image because they wrap around and show at the wrong DOA. Things don't disappear. They just wrap around. Very important. And again, that's another reason why the safe choice is to go with D that is lambda over 2. Then you cover the full 180 degrees. Stuff that's behind you, you don't even physically, hit them with your chirps. So everything that's in front of you, then you know that things don't wrap around, and that's your safe bet, basically. If you want to design a radar that physically does not see outside, say, 100 degrees, the only option you have is to design antennas with radiation patterns that are contained in 100 degrees. And then physically, you don't radiate outside that cone, and then you're guaranteed to not see targets that are outside that field of view. Then you can place them at a lambda bigger than lambda over 2 spacing. Make sense? Did I clarify your question about the F double prime? Okay, good. Okay, so let's see. So that's about the DOA resolution and the maximum field of view that you can get with this algorithm. Now again, I want to re-emphasize the fact that first of all, exactly every DSP step that we develop for the FMCW radar, range estimation, velocity estimation, and now finally angle estimation, these all turned out to be spectral estimation problems. And the FFT algorithm, again, it's the simplest, most efficient thing you can do, but in terms of performance, it is not the best performing algorithm, right? That's very, very important to note, and that means there's huge opportunity in the DSP domain to improve the performance of these types of radars. Now, specifically for the DBF method we developed, the digital beamforming that is FFTs, it's even more limited because of another fact, which is that algorithm is only compatible with uniform linear arrays. There are more general algorithms. Actually, in your homework, you will develop a better algorithm that works for any array, not just ULA, and you would see how that works. It's just an extension of our FFT algorithm, basically. Now, when it comes to DOA, specifically, there a lot of research efforts have been spent on better DOA algorithms on radar, because usually the resolution that you get from FFTs for range and velocity estimation is considered good enough for most robotic applications, but the resolution you get from the FFT for the DOA is really not that great. And especially, we just saw that it even degrades towards large angles, so it's very limited. So a lot of the research efforts have been in the algorithm space have been focused on super resolution DOA methods. So if you look at the literature, there's tons and tons of interesting algorithms that people have tried successfully to improve the resolution, DOA resolution of radars. Roughly, you can categorize them into three types of algorithms. There's quadratic methods like Capon. There's subspace techniques. These are very linear algebra-based and statistics-based methods like music and spirit. And there is more modern compressive sensing techniques like the iterative adaptive approach or the orthogonal matching pursuit, OMP. Very, very rich, interesting, active research area for those of you who are interested in radar DSP, and this still has a lot of room for improvement. We are not nearly there when it comes to really modern, interesting radar DSP. Just to give you an idea of like how much you can improve, let's say the DOA. Here there are two plots. The top one is the DOA that you get from our FFT method, right? So here we're just looking at the 1D DOA FFT, and the ground truth that we had two targets at theta hat 1, theta hat 2, and so your x-axis is theta, is the DOA, and the y-axis is the magnitude of the FFT that you get in dB. And here you see, yes, like your two largest peaks in this FFT are actually at the correct DOAs of the ground truth target. But if I just showed you this without telling you where the targets are or how many targets were in the scene, I mean, you might have said, I don't know, maybe this is also a target, maybe this is also a target, maybe this is also a target, or maybe this is also a target. So you might guess, or even like a CFAR algorithm might give you like 5 or 6 peaks instead of just 2 if it's not tuned perfectly, right? Now you use a better algorithm. So here is the iterative adaptive approach. Everything is kept the same. Same array, same waveform, same sampling rate, same everything. Only the DOA algorithm changed, and now look at the performance gain that you get. I mean, looking at the second one, it's absolutely clear that there's only 2 targets, and you can even by just comparing the width of the peaks, you can also tell that you get much, much better resolution. So you get better dynamic range by almost 10 dB, better resolution by a factor of 5 to 10. And IAA is not even that modern an algorithm. I mean, if you check the IAA paper that I've put in there, I mean, this is like, I don't know, 10, 20 years old algorithm. It's not even that new. So again, just to show you how much room for improvement there is when it comes to radar DSP. Okay, very briefly, we talked about just 1D DOA. Everything we did, we were assuming like a uniform linear array and just azimuth angle. 2D DOA, exact same. So if you have a 2D uniform linear array, like I've shown here, and a 2D, again, it's a spanning now in a plane, and then in each axis, the spacings are uniform. So they're, say your antenna elements or virtual antenna elements, in this case, are in the YZ plane. And in the y-axis, they're d sub y apart. And in the z-axis, they're d sub z apart. Okay, so that's like a 2D ULA. Then the exact same essentially algorithm is applicable, except you do it separately for azimuth and elevation. So you end up doing 2 FFTs for DOA. One gives you azimuth, one gives you elevation, and then everything works, and then you basically can do full 3D localization. I'm not going to go through the math because it's essentially the same as 1D, but it's in there, and you can go over it if you're interested. Okay, so just gonna skip here. And next topic is this idea of waveform orthogonality for MIMO radar. So when we developed this concept of virtual array, there was a implicit assumption in there, which is extremely important, but we kind of didn't talk about it till now, which was the fact that in our DOA processing, we assumed that the signals transmitted by different transmitter antennas are completely separable. And by separable, I mean basically the IF signals, which we called SIF of KQ, which correspond to transmitter number K and receiver number Q, all of those we assume that they're individually, without interference, accessible to our DSP pipeline. Okay, and we just basically called every KQ combination a virtual antenna, and then we work with the virtual array, right? So that's a very important assumption, because, for instance, if all the transmitters are transmitting at the same time, at the same frequency, the same waveform, there's no way the receivers can separate out which waveform that they received was coming from which transmitter, right? So for this separability assumption to hold, which is the underlying assumption of basically all of our MIMO DSP, essentially we need to have orthogonality between the signals that different transmitters transmit, okay? And again, by orthogonality, I mean perfectly separable. There's no overlap or interference between different transmitters. When it comes to orthogonality, there's different ways you can add that to the signals. So there's essentially 3 main techniques to orthogonalize the way the transmitters in a MIMO system. First one is time division multiplexing, or TDM, which is the simplest thing you can do. Basically, you don't run all your transmits at the same time. You sequence them. So transmit number 1 sends everything, if all other transmitters are silent, then number 2 sends is chirped, and number 3 sends a chirp, and so on, and then you repeat. Okay, so that's the concept of TDM. You can also do frequency division multiplexing. If the signals that are sent by different transmitters, the center frequency is different enough that they don't overlap in frequency. So the TDM makes sure they don't overlap in time. FDM, or frequency division multiplexing, makes sure they're separable in frequency. And the third one, which is code division multiplexing, basically uses special waveforms such that the waveforms themselves are orthogonal and separable. One example we have seen is, for instance, M sequences. We know that the cross correlations of different M sequences is almost 0, so they are separable, exactly as GPS does, right? GPS receivers can separate out signals that they receive from different satellites. So To ensure, again, separability, we need to orthogonalize the signals. You either do it in time, in frequency, or in code. Those are the three basically standard techniques. Most common one that is done today for FMCW MIMO is TDM. And that's the one I'll talk a little more about. FDM and CDM are not used much today. I hope we'll see more of them, mostly because they add complexity to the hardware. But TDM is just, hardware is the same. It just makes your DSP a little more involved. So that's the main reason. But in terms of performance, FDM and TDM can achieve better performance than TDM. So what is the TDM MIMO principle? So the TDM MIMO principle, again, very simple. We can just look at this picture here to fully understand it. So one frame of a TDM MIMO waveform, essentially, is broken into, remember for the case of a SISO system, we had M chirps in a frame. Now we have M, what we call chirp loops, from 0 to M minus 1. And what happens inside every chirp loop is exactly as I said, all the transmitters sequentially transmit. So first your TX1 sends the chirp, every other TX is silent. Then your TX2 sends a chirp, then your TX3 sends a chirp, then you're all the way to the TXN, and then you go to the next chirp loop and repeat. So the overall waveform that you get in TDM MIMO is like this. So I'm using different colors for different transmitters, and as you see, they are completely separable in time. So every receive antenna, when they receive an echo, they know exactly which transmitter it corresponds to because only one transmitter was active at that time. So TDM, basically, it's kind of trivial to separate out the signals and then construct your virtual array. However, as everything else, there is no free lunch. So it comes with a couple of trade-offs. First one is, of course, it makes your frame time longer, right? Because now we are time multiplexing between different TXs. So to send the same number of chirps, so to keep this M constant, same number of chirps per transmit antenna, if you do TDM, now your frame takes a factor of NTX longer. So if you have 10 TXs and you TDM MIMO them, then your frame time becomes 10 times longer, which means your frame rate is dropping by a factor of 10. Right? So that's the first trade-off. Everything becomes slower because you're sharing time. Okay, but it has even more important consequences. And the main one that basically becomes a big limitation of TDM MIMO is if you look at this picture here. Remember, so when we're looking at the data cube of our radar, we have different sampling rates, right? So you have your ADC sampling rate, that's your fast time axis, right? Those are like the rows of the raw data cube. And then you have your slow time, which if you remember, the sampling rate is the time between two consecutive chirps that are transmitted from the same transmitter. So if you look at your green transmitter, one sample here and one sample here, now that is our new slow time sampling interval. So if we do TDM MIMO, our slow time is going to become a factor of NTX slower, right? So the sampling rate in the Doppler axis is going to drop by a factor of NTX. What does that mean? If you remember the Doppler resolution and maximum velocity equations that we developed, the maximum Doppler frequency that you can detect, because it's tied to the FFT, is proportional to basically the inverse of your slow time, which is the sampling rate across the Doppler axis. Sampling rate drops, which means maximum frequency drops, so the maximum velocity that you can detect drops by a factor of NTX in TDM MIMO case. This can be, depending on your application, you might not care about it. If that maximum velocity is still acceptable, you're like, okay, fine, I'll just live with it. But in certain applications, this might be a blocker already. So say in autonomous driving, originally you designed your frame and chirp waveform parameters such that the maximum detectable velocity was 100 miles per hour. And now you TDM MIMO it with 10 transmitters. Your sampling rate across Doppler drops by a factor of 10, which means your maximum Doppler velocity drops by a factor of 10. Now from 100 miles per hour, you're down to 10 miles per hour. That's absolutely not acceptable for autonomous driving. I mean, everything pretty much on the roads is moving faster than 10 miles per hour. So that can become a big issue. So again, here's the math. Your maximum detectable velocity, originally, if you remember, it was lambda over 4 times t, where t was the chirp duration. That was for the case of a SISO system. Now for a TDM MIMO system, it becomes lambda over 4 times t loop, where t loop is the loop time, which is n number of tx's times the chirp time. So your maximum velocity, again, is dropping by a factor of ntx compared to the SISO case. Can be a huge problem. What can you do about it? Turns out there's a number of techniques. This is, again, one of those very active research areas for radar, but there's a number of techniques that you can use to essentially increase back the maximum velocity you can detect. Very briefly, what you can do, you can either design special antenna arrays that help you recover a larger, or unwrap your velocity FFT and recover larger velocities. You can design special waveforms that, again, enable you to recover large velocities in the case of TDM MIMO. Or you can basically design better DSP algorithms. So instead of just doing an FFT, you do something more sophisticated, which doesn't have the limitations associated with FFT. And a big limitation associated with FFT is, again, the maximum velocity you can detect is tied to the sampling rate. But there are other algorithms which don't operate that way, and then they can recover large velocities in the case of TDM MIMO. So again, TDM MIMO, very easy technique to basically give you separability or orthogonality between the transmitted waveforms in the case of MIMO, but this is the first limitation of it. It has a second, I wouldn't call it limitation, but a caveat that it actually is not highlighted enough in literature, and oftentimes people miss it, and the system still works with significantly degraded performance, so I just want to highlight that here. That is called phase from motion. So what this second thing is very briefly, if you look at one of these chirp loops that you do in a TDM MIMO configuration, again, remember that your transmitters are going sequentially. Your TX1 fires and TX2 fires and TX3 fires and all the way to TXN, okay? And if we look at our original signal model that we had on the board here, we said that the IF signal you get from virtual element number P, it has two components. It has this temporal component, SIF of T, and it has this spatial phase, which is e to the j omega IP, right? And we basically work with this e to the j omega I to recover direction of arrival. Now for TDM MIMO, there is a third term in the phase term in the signal model, which we call the TDM phase, and that is added because of the fact that your chirps are not sent at the same time from different transmitters. So each transmit index k, because it starts at a different point in time, the phase that you receive from that is going to be different from different transmitters. And that is this third term, which is e to the minus j2 pi. Ft is the Doppler frequency. K is the index of the transmitter antenna, not the virtual antenna, but the physical transmitter antenna. So it goes from 1 to ntx times big T, which is the chirp duration. So that's basically T. So more concretely, at the start of every chirp loop, you can assume that term is there's no phase for your first transmitter, but your second transmitter, because it starts T seconds later, there's this additional phase, e to the minus j2 pi fdt. Your third transmitter has a phase e to the minus j2 pi fd times 2t, and so on. If you don't, if I clean this up, if you don't model this term and compensate for it, it's just going to effectively corrupt your omega kq phase, and that means it's going to degrade your DOA, right, estimation. But it's extremely easy to compensate for this, right? Because after we do our range and Doppler processing, essentially we know this TDM phase term because we have found FD for every processed cell in the data cube, and K is just the transmitter index, which is known, and for every slice of the data cube. And big T is, again, the chirp duration. So this entire TDM phase term is known, and all you need to do to compensate for it is, after you do your range and Doppler FFTs, you do this additional step, which we are multiplying by e to the j minus that TDM phase to cancel it out. And per cell, you multiply by this term. It cancels out the TDM phase, and then you do your DOA FFT. Very simple step. It's just one complex multiplication. Extremely important. If you miss this, you're going to significantly degrade the DOA performance. Here's one example. This is very simple scene, just one target in the scene, and this is kind of the point cloud, if you will, 2D point cloud. Also, you can think of it as a range azimuth map of the target. So that's basically the target. That's what you get if you do proper TDM phase compensation. If you forget that step, multiplying by the inverse of the TDM phase, it still kind of sort of works. You do get a point cloud, but look how much blurred this is compared to. It's blurred. It's also not exactly at the right DOA. So if you compare this angle theta with this angle theta, you would see they're not the same. There's a little bit of rotation because, again, you have affected the phase. Extremely, again, important. Do not forget this if you're working with a TDM MIMO system. And I've seen textbooks that entirely miss this. They don't even mention that this is a critical step. And nobody knows because it kind of sort of works. It's just not as good as it could possibly be. Questions? OK. So again, this was one way of ensuring separability of the transmitted signals using the time division multiplexing concept. There's frequency division and code division multiplexing that I'm not gonna go over them because most standard hardwares don't support them anyway. But I hope we see more of them. The math and the explanations are in the notes if you're interested. OK, so we're going to basically close the radar chapter just with a few remarks. Radar, again, it's extremely useful, and there's a lot you can do with it. And the state of the radar today, it still has, across the board, from hardware design, antenna design, algorithms, waveform design, and by algorithm I mean ranging, Doppler, target detection, direction of arrival. Across the board, like any point that you put your finger on it still has a ton of room for improvement. So I really believe, like, in the next 10, 15, 20 years, we are going to see significant improvement in what radars can do. And as part of that, there's a number of challenges that I want to highlight that need to be basically figured out, and they're actively being researched on. One is the multipath effect. So multipath effect, essentially what it is that if you have big flat surfaces in the scene, your millimeter wave emissions can basically bounce off of them, kind of like they can act like mirrors almost, okay? So here, if you have like a radar on this blue car, ego vehicle, and the red is like the target in front of it, of course you would have this direct travel path of the millimeter wave, and that gives you the real target. But if it's driving on a road and you have like metal guardrails on the side, it can happen that you actually hit the guardrail, and you get reflected, hit the target, and then you take the same path back, right? And if you do your standard DSP on this, of course, the receiver DSP doesn't know that this echo that it received was from a multipath, so it just processes it, and it finds range and DOA, and it would, in your point cloud, it would show as a target that was there, which is a ghost target. It's at the wrong DOA and at the wrong range, and it's not even a physical target. So that can be a big problem. Again, depends on your application, like the environment that you're operating at. If there's, especially like indoors, it's horrible. Like in this room, if we were to operate radar, the ceiling, the floor, all the walls would create a lot of multipath echoes, so we would see a ton of ghost targets, for instance. And again, there's different ways. It's a very active research area, how you essentially detect and eliminate multipath. People have gotten very promising results, and you can do, special, again, antenna design, waveform design, or DSP. The other effect is mutual interference. So if you have two radars on two robots or two cars, so let's say the red car here has its own radar and the blue has its own radar, and they're pointing at each other, and the two radars are operating at the same frequency at the same time and sending the same kind of waveforms, then they can interfere, essentially like blind each other. Right, or even if not fully blinding, it can significantly raise the noise floor, for instance, because of a lot of in-band interference. So that can be a big problem. This is one of the areas where PMCW radar really shines, because again, as we know, these ranging codes that are used in PMCW, the M sequences, all you need to do is use two different M sequences, and then they're orthogonal, and they wouldn't interfere. FMCW really is not that good in this area. I mean, FMCW is kind of like analog waveforms that you're sending, so they can really interfere with each other a lot. And again, it's a very active research area. People have come up with very clever, algorithms to essentially mitigate this mutual interference. And the third one is a physical effect called spillover. And a spillover is basically direct coupling from a transmitter antenna to a receiver antenna without echoing from a target, right? So if your antennas have very wide radiation patterns, and if transmitter and receiver antennas are placed closely, which can happen on these microstrip antennas, signal can directly spill basically from the transmitter to the receiver, and then two things happen. One is because it's very strong, right? It's right, next to the transmitter, so you get a very strong coupling, and you eat into the dynamic range of your receiver. But also, if you process it, it might even show up as a target at a very close range, right? That could also happen. Sometimes some receivers apply what is called range gating. So they just ignore anything that is too close, and they say this is probably spillover. If it's like, I don't know, less than a couple of inches, they don't even show it or process it. But still, it can eat into the dynamic range. And best thing you can do is, if you're involved in the antenna design process, is to, in simulations, check for how much coupling you get between transmitter and receiver antennas, and ensure by design, by adding sufficient isolation and spacing between the antennas, ensure that this doesn't become a big problem. Okay? Yes?
What's an example of like adding isolation other than like putting them further apart?
So depends on what kind of, the question is, what is an example of adding isolation aside from just adding space? Depends on the type of antenna that you're working with. But again, if it's microstrip antennas like these little patch antennas on a PCB, if possible, one thing you can do is add ground in between. So let's say, I ran out of space. Let me sketch it again. So if this is a transmit antenna, again, microstrip on a PCB, if you add a bit of just like ground copper between that and a receiver antenna, that can add isolation. But again, there's no free lunch because if you add this ground, it will also affect the radiation pattern or the gain pattern of the antenna. Everything is a trade-off, right? So yes, you can add ground. If you add it too close, you reduce your coupling a lot, but you also affect the radiation pattern a lot. And then that can add extra complications. But it's a technique. It is used when you can. You add grounding to basically help shape it. The best thing is just a space. Like, as much as possible, don't place them too close to each other. Yeah. If you remember, or maybe later you can check on your slides, there was this TI PCB that we looked at. If you look at that, all the transmit antennas are at the bottom and all the receive are at the top with very big spacing between the two, and that's for isolation reasons, basically, so that you don't get much spillover. Okay, so that's pretty much it about radar. Again, I think radar is probably the main sensor for autonomy, which still has a ton of room for improvement across the board. And by across the board, I mean everything from algorithms, waveform design, antenna design, general hardware, even like the frequencies that the radars are operating at. As I told you, now people are researching like 120 gigahertz. I've seen researchers on 300-400 gigahertz. You know, it's just going to keep improving. And I just want to close this chapter by showing you a very brief part of a keynote video. This was delivered by the CEO of a company called Mobileye. Mobileye is one of the biggest companies developing sensing technologies for autonomy. So they develop all kinds of different sensors, vision systems, radars, LiDARs, very, very interesting company. And this is a part of the speech that their CEO gave at the Consumer Electronics Show last year. So this is from January 2022, relatively recently. And before I play it, basically the point he's making is the same thing I just said, that radar, we just have so far barely scratched the surface of what radar can do for autonomy. And that's the point of what he's going to say next. So I'm just going to...
So to give you an idea of the quality of data that is there, because reading radar output is difficult. It's not like reading image output or reading LiDAR output. So we trained two networks. This is not actionable. This is just to show what this radar can do. We trained a network that was trained on radar input, LiDAR output. So we put a radar and a LiDAR together, and then we used the LiDAR as output for a neural network to map the radar to LiDAR. So what you see here is, on the left-hand side, the scene from a true LiDAR. On the right-hand side, the mapping from our radar. This neural network maps the radar output to a LiDAR representation. And as you can see that they're almost equivalent. Let's look a bit more. Let's start looking at the left-hand side. So on the left-hand side, I'll run this. Left is true LiDAR. Right is the mapped radar to LiDAR representation. It looks almost identical. So the point I want to make here is not the beauty of this neural network that we designed. There's nothing special about that neural network. The point I want to make here is the quality of the radar data. If you can take that radar data and generate a representation that's almost equivalent to a LiDAR representation, it means that there is gold to extract from this LiDAR. Let me show you on the right-hand side.
Okay, I'll stop here. You can watch the full video online. But again, the point is basically, as he said, there's gold to be extracted from raw radar signals. And the way to extract it, by the way, I don't think is what they did, and they even mentioned what they did is not actionable. It was just to demonstrate by training a neural net that yes, there is gold in there, but to really extract it requires, really deep knowledge, starting from the first physics principles and really, you know, across the board, as I said, from antenna design to every step of the DSP, really get deep and see what's the best that you can do. And I'm 100% sure, like, soon we're going to start seeing radars with outputs of this quality, which you can barely tell from a LiDAR. Okay, and that's a nice segue into the next chapter, which is going to be about LiDAR. But before that, any questions about radar? Okay, good. So LiDAR, again, we're going to do it the same way we did every other chapter. Start with a little bit of history, then we talk about the physics of it. From the physics, we build up a system architecture. We look at the system architecture, and then finally we look at, we develop a signal model, and we look at the signal processing algorithms for LiDAR. So LiDAR stands for light detection and ranging, or also some people call it laser imaging detection and ranging, but it's basically a sensor that uses laser beams for mapping. Okay, so radar used radio frequency electromagnetic waves. LiDAR uses optical frequency electromagnetic waves for mapping. And just like radar, it can determine the distance or range and the angle or direction of arrival to targets. And some LiDARs, as we'll see, can also detect radial velocities of objects, like for instance, FMCW radar can do. Now, where did it all begin? The idea has been around for a very long time, even before lasers were discovered or invented, like in the 1930s. I think Edward Sinch first proposed this idea of using a searchlight, so basically collimate a very powerful light and make a beam that you can shine to the sky, and then based on the light that hits, say, like aerosols in the atmosphere, part of the light scatters back, and then by just pointing a camera at the scattered light, for instance, you can determine the density of the atmospheric particles from the intensity of the scattered light. So that was, you know, a very high level concept of the searchlight that was proposed in the 30s. And then about the same time, Lebedev proposed the idea of, instead of just shining a beam of light, what about sending short pulses of light? And again, this is pre-laser days. But if you send short pulses and look at the reflected echoes of those pulses, and here by echo, this is optical echo, of course, you can measure the time of flight. So he basically proposed the idea of time of flight measurement using optics. A few years later, in 1936, some very successful experiments were done. Again, this was done with visible light, but people could measure ranges up to 3.5 kilometers with very decent accuracy, 2 to 3 meters, using this idea of send a short pulse of light, and then collect back the echo and measure basically range from time of flight. Then fast forward 20-something years, in 1960, the first laser was invented. And then soon after that, people kind of like put the two ideas together. So lasers, what they're really good for is making very short pulses, and you can also collimate them, as we'll see, very easily. So you can make very narrow beams of lasers, and also you can send very short pulses. So people started, almost immediately after the laser was invented, first applications, people were thinking of laser rangefinders. So rangefinder is like a very, very simple LiDAR where it doesn't give you a full map, it just measures the range to one point, right, from this time of flight measurement. And a few years later, I mean, from the early 60s, even like commercial laser rangefinders started hitting the market. The first one was from the Hughes Aircraft Company. Very soon after that, actually, Stanford got into the game. The Stanford Research Institute here in Palo Alto, they started doing the first LiDAR experiments. Again, these were not 2023 LiDAR that gives you like a nice 3D point cloud. These were just laser rangefinders. But people were essentially, the core concept and the physics is the same. And then Swedish Army got into the game. The Soviet Union started basically building rangefinders, and especially for military applications and also for meteorology, it started basically becoming commercialized. And then it was a little later in the 70s and the 80s where more applications of these still rangefinders, but you can't think of as early lidars. More applications started becoming basically common. Wind measurement, missile guidance in the military, mapping of the polar ice caps, for instance, and police speed guns. We're using basically short pulses of laser and the early LiDAR concepts. But it was only at the 1990s where the modern day imaging LiDARs, which give you these very nice high resolution 3D point clouds, started to become commercial. So in comparison, imaging LiDARs are a much modern, although again the core idea was thought of in the 30s, it wasn't until the 90s that the technology maturity was at the level that these modern day imaging LiDARs could be developed. And in that sense, it's a much younger technology compared to, say, radar or sonar or other things we have talked about. So here are some pictures. These are from the 1930s, the early rangefinder LiDARs. This is the SRI Mark I LiDAR. SRI is, again, Stanford Research Institute, so this might be somewhere in Palo Alto, actually, this picture. Again, these are these huge systems, and there's like a transmitter and a receiver, so one sends the pulse, the other one receives the pulse, and then there's a lot of equipment to control the laser and also process the received echo to measure range. So this would just give you like one range measurement. This is SRI Mark II, and this is the one that the Howard Hughes aircraft company made. It kind of looks like a rifle, interestingly, and it's called the Hughes Collider Mark II was the marketing term they were using. And it was like a portable, basically rangefinder thing. Here I have a modern rangefinder. You might have seen these. Let's actually power it on and take a look at together. Again, it does the exact same thing. So this is not a LiDAR. It's just a rangefinder. If I can turn it on. Okay. So this one, it comes with a red laser pointer. So the red is just the red laser. They don't use it for ranging. It's just for aiming. So I know where I'm pointing at, and then if I hit it, then it gives me the distance, 8.65 meters. Okay. So again, this is not a LiDAR, but you see, like, because if you can do this, you can also make a LiDAR. If you do this fast enough and you like scan your beam, and you do like one range measurement per position, and then for each range measurement, I also know where I'm pointing at. So the DOA is kind of trivial for LiDAR because the beam is so focused. I just need to know where I'm physically pointing it to. I don't need to do complex DSP. And you just like scan it and do a bunch of range measurements, and then you build basically a 3D map. And that's how essentially LiDAR works. So you can kind of see from here that the DSP is going to be much more simple than radar, for instance, because part of the complication of the DSP for radar is the fact that, especially for MIMO radar with microstrip antennas, you have very wide beam patterns, so you receive echoes from everything in the scene at a very wide field of view, and then you have to like untangle everything and figure out the range of every target, the DOA of every target, and the velocity of every target in DSP, versus in LiDAR, you pretty much can assume the signal that you receive at any point in time is coming from just one target because your beam is so focused. It's just millimeters, wide, and it's very, very localized. So this is the 30s. Now fast forward to 2020s. Now, of course, we have much better LiDARs. You can get very high resolution 3D maps from them, like this one from Stanford campus. And they're used in many different applications: oceanography, meteorology, even like some cell phones these days have built-in little LiDARs that are used for AR, VR applications. And of course, in autonomy, especially in self-driving or autonomous vehicles, LiDARs are one of the key enabling, basically, sensors. Okay, so LiDAR physics. Very briefly, again, as I just showed you with the rangefinder, the principle of operation is extremely simple. You have a laser source, okay? So it generates a laser for you. It goes through TX optics, and by optics I mean just lenses, right? What the lenses do, as we'll see, it will basically make this nice collimated narrow beam of laser for you that doesn't diverge too quickly. So then you get this pencil beam that goes and hits a target, and then you get this part of the light echoed back or reflected back. And then on the receive side, you also have some optics or lenses, and then the optics basically focuses the received light echo into a photodetector. And from the photodetector, we get some signal waveform out that we can pass to our DSP, and then basically estimate range and possibly velocity. So again, exact same principle of operation as radar and sonar, but operating at different wavelengths, and because of that, it comes with very different performance metrics. You also want to basically scan your transmitter beam. As I said, you want to keep aiming it at different locations, and you want to do this very fast. I mean, LiDARs today, good ones can give you multiple million measurements per second, like 2 to 5 million points per second, basically, is what modern day LiDARs operate at. And so basically, we're going to study this starting from the physics. We'll look at laser physics first. Then we talk about these beams, which are called Gaussian beams, and how they're generated, how they behave. We talk about the optics, which basically collimate the beam for you. And then we talk about the principles of photodetection. What is a photodetector? How does it work? What is the physics of it? And then once we do that, we basically can complete our system architecture, and then we build a signal model for ST. And finally, we talk about DSP. Exact same story as we did for radar and sonar. I think this is a good place to stop, and then we will continue next time.